Curves in industrial design. Bezier curves and their properties. A Bezier curve of degree n is a polynomial curve of degree n parameterized in terms of the Bernstein polynomials of degree n and the n+1 control vertices for t between 0 and 1. The Bernstein polynomials are expressed in this way: the binomial coefficient that multiplies 1 minus t to the power n minus k times t to the k, for k a natural number between 0 and n. Each point of the control polygon is called control vertex. The points of the Bezier curve are always barycentric combinations of the control vertices, because by the binomial theorem, when we add up the Bernstein polynomials, all the Bernstein polynomial of degree n, we are adding up these numbers, which is, by the binomial theorem, 1 minus t plus t to the nth power. Because t minus t and t cancel out, we have 1 to the n power, which is 1. So the Bernstein polynomials of degree n, they all add up to 1 for any t. Bezier curves have properties that make them useful for design. They depend on a small data set. A Bezier curve of degree n is completely determined by the ordered set of n+1 vertices of its control polygon. The degree of the curve is always 1 less than the number of the vertices. Control polygon. The curve always starts and ends at the first and last control vertices. Here we see Bezier curve of degree 3 that starts in the first control vertex and ends in the last control vertex. The curve is tangent to the first and last edges of its control polygon. So we can see here how the curve is tangent to this first edge of the control polygon and tangent to the last edge of the control polygon. The shape of the Bezier curve is roughly the same as the shape of its control polygon. We can see that this is the control polygon, and basically the Bezier curve follows the same shape in a smoother way. And finally, when moving a vertex of the curve changes mainly near that vertex. So here we are going to move the vertex C2 and we see how the curve has changed its shape, but mainly near C2. So on the screen we can see the control polygon of the cubic Bezier curve, and we can see how it moves when we move control vertices. The whole move curves, but mainly near the control vertex we are moving. It always, even when we move the vertices, it always starts at the first control vertex and ends at the last control vertex. And always, even when we move the vertices, the curve is tangent to the first and last edges of its control polygon. The curve is symmetric with respect to the control polygon. That means that the curve with control polygon C0, C1, Cn is the same curve as the curve with control polygon in the reverse order, Cn, Cn-1, C0. What changes is the orientation of the curve, but not the curve itself. This is due to the symmetry of the Bernstein polynomials. Here we can see the Bernstein polynomials of degree 3, and we see how the first Bernstein polynomial of degree 3 is symmetric to the last Bernstein polynomial of degree 3, and how the second Bernstein polynomial of degree 3 is symmetric to the third Bernstein polynomial of degree 3. This symmetry is represented mathematically in this way. The k+1 Bernstein polynomial of degree n evaluated at t is equal to the n minus k+1 Bernstein polynomial of degree n evaluated at 1 minus t. On the screen we see on the left a Bezier curve with control polygons C0, C1, C2, C3 and C4, and on the right we see a Bezier curve with control polygon the reverse of the control polygon we saw before, C4, C3, C2, C1, C0. So in this case this is the first control vertex and this is the last control vertex. So the parameterization of the curve on the left is C0 multiplying the first Bernstein polynomial of degree 4 plus C1 multiplying the second Bernstein polynomial of degree 4 and so on, whereas on the right we have C4 multiplying the first Bernstein polynomial of degree 4,
C3 multiplying the second Bernstein polynomial of degree 4, and so on. The way the curves look is the same, so they describe the same curve in the plane, but the parameterizations are different. We can see that by showing how a point moves on the curve. So when t is equal to 0, the point P, or C of 0 in this curve, is C0, whereas on this curve, when t is equal to 0, the first point is C4. It corresponds to the first point in the control polygon. As t moves on to 1, the points move on the curve in reverse order.
Curve localization. The Bezier curve is contained in the convex hull of its control polygon. So here we see a Bezier curve of degree 4, and this is the convex hull of the control polygon of the curve. This is due to the fact that the points on the curve are barycentric combination of the vertices of the control polygon. Invariance under affine transformations. A Bezier curve can be translated, rotated, or reflected without changing its shape, by translating, rotating, or reflecting the vertices of its control polygon. Again, this is due to the fact that the points of the Bezier curve are barycentric combination of its control vertices, and this property is preserved under affine transformations.
On the screen we can see a Bezier curve of degree 5 and its control vertices. This is the first control vertex, and this is the last control vertex. So we can rotate the curve by an angle 1/4, for example. We can reflect the curve by just reflecting and translate the curve by just doing these operations on the control vertices. And the curve doesn't change.
Variation diminishing property. The Bezier curve twists less than its control polygon. A planar curve intersects a given straight line no more often than its control polygon intersects the line. Spatial curve intersects a given plane no more often than its control polygon intersects the plane. So here we see a Bezier curve of degree 5 with its control polygon. And this is the Bezier curve. Here we see a line. The number of points in the intersection of the straight line with the control polygon is 4. 1, 2, 3, and 4. And the number of points in the intersection of the curve with the straight line is 2. 1 and 2. If we move the line, for this line we keep having 4 intersections with the control polygon and 2 with the curve. And here we have 2 intersections with the control polygon and 2 in the curve. Here the same, and again the same. This line here intersects the control polygon in 2 points, one on the segment from C4 to C5, and another point in the segment from C2 to C3.